All right, welcome everyone to our second pre-class video on 3.9. Here we're talking about initial value problems and applications. We're still in the antiderivative section, so there's going to be a decent amount of antiderivatives going backwards with our derivatives. But now we're going to use these to solve particular initial value problems, which I need to give a definition for that still, and then also use these to actually solve some real world kind of questions. And so to that end, why don't we get started with our first example here, a nice little example. We have a ball that we're throwing up in the air. Its velocity is given by 7 minus 10 t meters per second, t seconds after the ball is released. So we have some velocity function there. If the ball is initially 1 meter above the ground, find the ball's position s of t. Now, the first thing that we have to remember is that the derivative of our position is velocity. So essentially what we are given here is a derivative, right? It's a little f, and we want to find an antiderivative. We need to figure out where we started, what was s of t, in order to get this particular velocity. I suppose let's go ahead and write this down. And so just like we did in our first video, we need to kind of go backwards. We need to take an antiderivative here. And so let's think about how would we get 7 minus 10t? Well, I think, and again, our variable here is t instead of x, so I'm going to be using t's. But for instance, if I wanted to get 7 after taking the derivative, I would start probably with 7t, right? Because when you take the derivative of t, you would just get 1. Next up, if I wanted to take the derivative and get 10t, remember this is 10t to the first power, I would think of this probably as there's this constant minus 10, and then I'm going to be thinking about the power rule. So I would start off with maybe something like t squared, for instance, and when I take the derivative of that, thinking about getting back to where I started, I'd get my 7t, of course, and then I would have what, 2t to the first power. So I like that t to the first power, but I don't like the fact that there's a 2 now there, right? I shouldn't have that. It should just be 10, not 20. So in order to cancel a little bit, I'm going to need this 1/2. And maybe you're already doing this in your head and you don't need to kind of break it up in this many steps, but at least for this video, I figured I'd take it a little bit slow. And then yes, you will get faster with this. So again, if there's a 1/2 there, now this will perfectly cancel out and we will get to what we started with, in this case, negative 10t. So all that looks good. Of course, if we want to go ahead and simplify this and do the most general antiderivative, it would look like 7t minus 5t squared plus some constant, right? And again, this can be any old constant. 0 is perfectly fine, but it could be 5, it could be 3, right? All of these are perfectly good antiderivatives for our velocity, aka position. Okay, so now we need to know, right? We have this extra condition here that the ball is initially 1 meters above the ground. And so we need to figure out maybe what C value corresponds to that. And so initially, this usually corresponds with time equals 0. So at time 0, we know that the position ought to be equal to 1, right? The height above the ground ought to be 1. And so when I plug in 0, I should get out a height of 1. And so let's go ahead and do that into my function here. So if I plug in 0, I'd have 7 times 0 minus 5 times 0 squared plus c. And my position, my height, right, should be 1. So there's my output. And so you can see that this helps us solve for which antiderivative I actually want. In this case, it's going to be the one where c is equal to 1, because that gives me an initial position of 1 meter above the ground. And so with these initial value problems, it's not only about finding an antiderivative, but it's then using some well, initial condition, or right, there's some value given to us that we can solve for that c, this unknown bit. And so my final answer after I plug this in would be, and I'm kind of running out of room, so I apologize. I'll just kind of squeeze it in down here. S of t, 7t minus 5t squared. And instead of plus c, we're going to have plus 1. So this would be my final answer. This gives me the fact that the ball is 1 meter above the ground to start. When I plug in 0, I get out 1. But also when I take the derivative of this, I get the correct velocity function. All right, so now that we've had a bit of a motivating example, right, let's go ahead and talk about these things in general and get some definitions. So first off, a differential equation is an equation involving derivatives of an unknown function. So quite often the game is trying to figure out what that unknown function is. And then an initial value problem is a differential equation for y equals f of x along with some initial condition, such as f of c equals a for some constants c and a. And then the solution to the initial value problem is the solution to the differential equation that also satisfies the initial condition. So this last problem here, we solved an initial value problem, even though we weren't necessarily calling it that, right? We were given some equation that had a derivative. So in this case, we had s prime of t was equal to 7 minus 10t. So there is a differential equation, and we had some initial condition. So that is that when I plugged in 0, I ought to get out 1 for my height or my position right above the ground. So that was my initial condition. And then with those two, we solved for that unknown function, right? What is the full position function? And that gave us our final answer here. So we now see that this is, solving an initial value problem. And now I'd like to do this kind of, with a pure math problem. So here's a setup, solve the initial value problem. So again, our ultimate goal here is trying to find some function f of x. Right, I'd like to kind of go backwards here. I'm given an equation that has a derivative in it, right? In this case, f prime of x is equal to 1 plus 3 root x. And I have some initial condition. In this case, when I plug in 4, I ought to get out 25. So I'm trying to find a function that satisfies both of these conditions. All right, so let's go ahead and try this one out. I'm going to start off by doing a bit of a rewrite similar to what we did in our first video, right? Because we're trying to solve some antiderivative, right? I've started off with a derivative. I'd like to kind of find out an antiderivative, right? Where did this start off as? And so I'm going to do a rewrite because I'm thinking already about using the power rule. So first of all, I need something that when I take the derivative of it, I get 1. So that's, of course, going to be 1x, right? When I take the derivative of x, I get to 1. And then something that when I take the derivative of it, I get 3x to the 1/2 or 3 root x. Well, going a little bit faster now because we have done a similar sort of problem already. I know that I'm going to start off with bringing this 3 along for the ride, and I'm going to raise my power by 1, right? So I'm going to go x to the 3/2. And then I think I'm going to need maybe a 2/3 here. But let's go ahead and double check. Again, this is based off of me doing the problems from our last video and kind of getting decent at those. But when I take the derivative, let's check and make sure that I get back to where I started. So when I take the derivative of x, I get 1. And when I take the derivative here, let's see, we have a bunch of constants. Those are along for the ride. And then the derivative of x to the 3/2. Well, we'd have the 3/2 coming down, and then I'd reduce my power by 1. So notice that by having this reciprocal here of 3/2, these will nicely cancel out. And what I'll be left with is 3x to the 1/2. So that's exactly what I started with. So yes, this is a good looking antiderivative. So if I wanted my final answer, just like I did in the last video here, let's do a little bit of simplifying. The 3's would cancel out and I'd have 2x to the 3/2. And with it being a most general antiderivative, I'd have plus c. So this is my most general antiderivative. These are the problems that we solved in our last video. But now we want to solve this initial value problem, right? We have some condition. In this case, we want to make sure that when we plug in 4, our function outputs 25. So again, this is my f of x. It's kind of a long equal sign here, but f of x. And when I plug in 4, I want to get out 25. So let's go ahead and do that. So if I plugged in 4, I'd have 4 plus 2 times 4 to the 3/2 power plus c. And I'm supposed to get out 25. So that's supposed to be my f of x, right? When I plug in 4, I get out 25. All right, so I need to do a little bit of simplifying here. And 4 to the 3/2. So we can maybe know these rules of exponents very well, and you can see that this is going to be an 8. You can also plug this into your calculator or into Desmos or online calculators, things like this. But essentially what we're doing is that we need to take a square root, that's the 1/2 power, and we need to cube it. And so the order is really up to you. You can do this in either order. So the division by 2, the square root of 4 is going to be 2. And then when I cube 2, I'm going to get 8. So that's how we do this, kind of using our algebra rules. But again, you can plug this into a calculator as well and get the same result. So let's see, we're going to have 4 plus 16, I suppose. So this is going to be 20 is all that simplified plus our constant. And again, after all that, we should get 25. So subtracting 20 on both sides, I hope we all get that our constant ought to be 5. And so my final answer, right, a function that satisfies both of these is going to be x plus 2x to the 3/2 plus 5. So again, I was going back to my function that I had right up here, and then now I know what my constant should be, and we ought to make that 5. Now, of course, you can double check if you're at all paranoid, right? You can plug in 4 to this and verify that you're getting out 25. And you can verify that when you take the derivative of this, you get back to where we started. In this case, this 1 plus x to the, 1 plus 3x to the 1/2. All right. Well, maybe I should shade in my final answer here. And there we go. All right, let's do another one here, in this case related back to kind of more physical phenomenon, and that is we have some particle moving, again with a velocity, and we have some initial position, and we'd like to find the position function. So again, we need to remember that velocity, this is a derivative function. We are given a derivative, and our goal is ultimately to find the position. So we want to go backwards, not taking a derivative, but taking an antiderivative to get to position. So I need to think about, okay, what, when I take the derivative of it, gives me sine? Well, I know that when I take the derivative of cosine, I would get negative sine. So I think I need negative cosine. So, and you can of course double check when I take the derivative of this negative would be along for the ride. And then I would have the derivative of cosine is going to be negative sine. So minus a negative would be plus. So yes, that works out perfectly well. And then something that when I take the derivative of it, I get negative cosine. Well, I know the derivative of sine is cosine. So the derivative of negative sine ought to be negative cosine. So double check when I take the derivative of this, I get negative cosine. So yep, that seems to be working out well. For the most general antiderivative, I'd go ahead and have a plus c, and then I would like to find this initial position, right? Or well, sorry, I have an initial position that when I plug in 0, I should be at the point 0, the position 0, and I want to know what the full position function is. So, okay, when I plug in 0, that's going to be negative cosine of 0 minus sine of 0. This says that I should get out a position of 0. So again, when I plug in 0, I get out 0. All right, well, cosine of 0, our calculators will verify for us that this is 1, so that negative along with it becomes negative 1. Sine of 0 is 0. So when I solve for c, I get c is equal to 1. This is important because sometimes folks, they do a lot of these problems and they see that, oh, I need to get out 0 when I plug in 0. That means that my c value should be 0. But no, that's not the case. You really do have to solve these out in order to figure out what your c value is. And so don't try to take shortcuts, actually just plug it in and solve for c, because sometimes it is different, like in this case. So my final answer after all is said and done, we have negative cosine minus sine plus 1. And you can double check when you plug in 0 into this, you do get out 0. And if you take the derivative of this, you get back to that velocity function that we were given at the beginning. So this right here would be my final answer. All right, that's it for our pre-class video. I hope you guys enjoyed. We will expand on this and do more examples in our class time. But yeah, I'll see you then.